Hello everyone, and welcome to our video on the sum and difference formulas. So we're going to start out by looking at the sum and difference formulas for cosine, and then we'll start looking at the sum and difference formulas for other trigonometric functions. So we're going to go ahead and prove the difference formula here, but let's just take a look at these two formulas. Cosine of u plus v equals cosine of u, cosine of v, minus sine of u, sine of v. And cosine of u minus v equals cosine of u cosine of v plus sine of u sine of v. So the proof for this is a little bit long just because there's some algebra that we have to write out very carefully, but it's actually a very simple idea. So let's take a look at that idea. Again, we're looking at the proof for 2, and then we'll see that 1 follows immediately from 2. So the proof of 2, consider two angles u and v. So we've drawn the angle u here in blue and the angle v in orange. The angle between them is u minus v, right? We take all of u and we subtract the v portion, so that makes this angle u minus v. And notice here that we plotted 2 points on our circle, and those points by definition on the unit circle would be cosine of u, sine of u, and cosine of v, sine of v. Right? They are the terminal point associated with the angles u and the angle v, so those are their x and y values. Now, we're going to take a look at what happens when we place u minus v in standard position. So just imagine you're taking this angle here, the u minus v angle, and you're just rotating it back to where the purple side here is now on the x-axis. So now this is our angle u minus v, and so our terminal points are here, the positive x-axis at 1, 0, and cosine of u minus v, sine of u minus v. The key to this proof is to realize that if you take this angle and you just rotate it to the positive x-axis, that doesn't change the length between the terminal points, right? It's still a triangle that's got two sides that are equal. They have radius 1. They share the same angle u minus v in between them. Side angle side theorem from geometry tells us these are the same triangles, right? Rotating them doesn't change that, so the length between these two terminal points is the same. So that's the whole crux of our argument for this formula, is just understanding that the length between the points P and Q and A and B are the same. So now we just have to work out the algebra for that. So the distance between P and Q is equal to the distance between A and B. Now, in order to make this computation simpler, we're going to use the fact that if the distance is equal, then the distance squared between the points will be equal. And so again, we have a lot of algebra to do here, so we're going to take this equation and we're going to simplify one side at a time, and then we'll set the two sides equal. So we're going to start with the distance between P and Q squared. So that's the square of the square root of cosine of u minus cosine of v squared plus sine of u minus sine of v squared, right? That's just our standard distance formula. If you're a little rusty on that, just remember the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared, which is really just the Pythagorean theorem. Right? But solved for the third side. So again, when we look at P and Q, the x and y is cosine of u sine of u for P and cosine of v sine of v for Q. So all we're doing is taking those x and y values, plugging them into the distance formula. Okay, so here we've got our square root squared of this thing. The square root and the square cancel, so this is really just cosine of u minus cosine of v squared plus sine of u minus sine of v squared. And when I multiply all of this out, this first term, cosine of u minus cosine of v, multiplies out to this, cosine squared of u, minus 2 cosine of u cosine of v, plus cosine squared of v. And then the second term here multiplies out to sine squared of u, minus 2 sine of u sine of v, plus sine squared of v. And now we're just going to do a little bit of rearranging here. Cosine squared of u plus sine squared of u, we're going to write those together out in front here. And cosine squared of v, let me change the color here. Cosine squared of v plus sine squared of v, we'll put that next. And then what do we have left? We've got negative 2 cosine u cosine v and negative 2 sine u sine v. And so here we've just factored the negative 2 out of those terms. That gives us negative 2 cosine u cosine v plus sine of u sine of v. And of course, cosine squared of u plus sine squared of u is 1. That's the Pythagorean theorem. And cosine squared of v plus sine squared of v is also 1. So altogether, this simplifies to 2 minus 2 times cosine of u cosine of v plus sine of u sine of v. Now keep in mind, so far all we've looked at is the distance between p and q. Now we need to look at the distance between a and b squared. And just remember, a is the point 1, 0, and b is the point cosine of u minus v, sine of u minus v. Okay, so let's move on to that. So the distance between a and b squared is the square root squared of cosine of u minus v minus 1 squared plus sine of u minus v minus 0 squared. The square root and the square cancel, and I get cosine of u minus v minus 1 squared plus sine squared of u minus v. Right? That 0 doesn't do anything, so we just get sine squared. Now, once you multiply out this first term, cosine of u minus v minus 1 squared, get cosine squared of u minus v minus 2 cosine of u minus v plus 1 plus sine squared of u minus v. And so if I combine my cosine squared and sine squared together out in front, I can rewrite this as cosine squared of u minus v plus sine squared of u minus v plus 1 minus 2 cosine of u minus v. Cosine squared of this angle plus sine squared of this angle is 1. 1 plus 1 is 2. So this is 2 minus 2 cosine of u minus v. So now if we take these two sides of the equation, the distance between p and q squared, and the distance between a and b squared, and we set them equal, we get 2 minus 2 times cosine of u cosine of v plus sine of u sine of v equals 2 minus 2 cosine of u minus v. The 2's cancel out. Then we have negative 2 times this expression equals negative 2 times cosine of u minus v. Divide negative 2 across, those cancel. And we get left finally with cosine of u minus v equals cosine of u cosine of v plus sine of u sine of v. Okay, so again, the algebra is a little bit long, but the idea is really, really simple. The idea is just, hey, if I look at this angle u minus v in its position between the angles u and v here, and then I look at that same angle rotated onto the positive x-axis, the length between the points A, B, and PQ here are equal. Do some algebra. Once you do that algebra, out pops this nice formula here. So now, when we look at the cosine of u plus v formula, how are we going to deal with that? Well, we actually just use the formula we just derived. So here, cosine of u plus v, we can find that by taking and rewriting this as cosine of u minus a negative v, right? That's the same thing. But now, when I plug into my previous formula, I can write it as cosine of u, cosine of negative v, plus sine of u, sine of negative v. And then I just have to remember two little facts. that cosine is an even function, so cosine of negative theta is equal to cosine of positive theta, and sine is an odd function, so sine of negative theta equals negative sine of theta. So applying the even property for cosine lets me rewrite cosine of negative v as just cosine of v here, and sine of negative v as negative sine of v. So that's why the only thing that changes in these formulas is we go from a negative to a positive and vice versa, right? All that switches is the sign in between them, because when you plug in that negative angle, the cosine one is even, so that ends up just essentially disappearing, and the sine is odd, so that flips your sign in the middle around. Now, I'm not going to derive the sine and cosine formulas at this moment. You'll see that those are essentially, or you can see that those are essentially derived from the cosine formulas by essentially taking one of your angles and writing it as a sum of two angles. So it's a little bit of a tricky algebra step, but it's really just adding extra algebra to the process. So here, let's just look at all of these summarized, and then we'll talk a little bit about why these are written in a very particular way, which is to help them be a little bit easier to memorize. So cosine of u plus v equals cosine of u cosine of v minus sine of u sine of v. Cosine of u minus v equals cosine of u cosine of v plus sine of u sine of v. So the only difference here is that when I go to the difference formula for cosine, my sign in the middle switches to plus. Now for sine, that formula is a little different. Sine of u plus v equals sine of u cosine of v plus cosine of u sine of v. And sine of u minus v is equal to sine of u cosine of v minus cosine of u sine of v. Again, the only difference between these formulas is that the sign in the middle switches. Now, we can derive the tangent formulas by just taking the sine divided by the cosine and then doing some extra algebra simplification. Again, for time, I'm going to skip those, but you find those formulas with some pretty basic algebra. Now, when we take a look at these, what do we see? Tangent of u plus v equals tangent of u plus tangent of v divided by 1 minus tangent of u times tangent of v. And then when we look at tangent of u minus v, we get tangent of u minus tangent of v over 1 plus tangent of u tangent of v. Okay, now that's going to seem like just a whole lot of like things being blasted at you all at once. But here's some patterns we should notice that in the way we've written these intentionally to make them a little bit easier. We always write these formulas. Let me just color code these a little bit. It'll help it stick out. Oh, I missed a whole bunch of green ones. A whole bunch of the U's. There we go. Okay, so if we take a look at these formulas, what do we notice? We should notice that every single one of these is written in a form so that we get UV, UV, UV. UV, UV, UV. UV, UV, UV. UV, UV, UV. Every single time. Again, that's just one of those little things to help make these a little bit easier to memorize. Because we can, of course, multiply in any order we want. But by writing them consistently in this way, it'll be easier to reproduce them accurately, right? So UV, UV, UV every time. And then you can try to think there's a little bit of a a sort of pattern to how these work. So the cosine formulas, cosine, cosine, sine, sine, the sign in the middle is opposite, right? So when I look at the sign in the middle for the cosine formula, it's always the opposite of whether I have a sum or a difference formula. And for sine, it's sine, cosine, cosine, sine. The sign in the middle is the same. And for tangent, it's tangent plus tangent over 1 minus tangent tangent. So here, the sign up top is the same. The sign on the bottom is opposite. So cosine, cosine, sine, sine. Sine, cosine, cosine, sine. Tangent plus tangent over 1 minus tangent tangent, or plus tangent tangent. So hopefully that'll just help you structure a way of memorizing these a little bit better in your head to keep them straight. Okay, so below we've got a whole bunch of cofunction identities. Now, these cofunction identities can all be derived from the sum and difference identities. Now, we actually can also derive these cofunction identities from just the unit circle properties, right? But this gives us another way where we can algebraically confirm these identities. So I'm just going to do one of these as sort of a mini example off to the side. So sine of pi over 2 minus x. So I'm going to apply my difference formula for sine. And so the way I'm going to write this, I'm going to go sine, cosine, cosine, sine, and the sign in the middle is the same for sine. And now I just write my angles, right? UV, UV, UV. Pi over 2, x, pi over 2, x. All right, so boom. Sine of pi over 2 is 1. Cosine of x minus 0 times sine of x. That's cosine of x. And you can easily plug all of these identities into those formulas and derive the rest of them. Okay, so now we're going to see how we can apply these formulas to find the exact value of trig functions for various, let's say, unusual angles. So you should recall from our video on the unit circle that we chose the angles that are labeled on the unit circle because those are the angles that are easy to evaluate sine and cosine for geometrically. We could draw some nice little triangles and use some basic geometry to evaluate sine and cosine for those particular angles. Now, of course, when we're talking about applications of these functions, the world is not always 30 degrees, 45 degrees, and 60 degrees, right? So we need to be able to evaluate these functions in terms of other angles. So how did we initially build let's say a repository of data on these trig functions? Well, we used these sum and difference formulas. So for example, if I want to find the value of sine of 15 degrees, I can notice that I know values for trig functions of 45 degrees and 30 degrees. And 45 degrees minus 30 degrees is 15 degrees. So that means I can rewrite sine of 15 degrees as sine of 45 minus 30 degrees. And that allows me to apply the difference formula. And so again, this is sine, cosine, cosine, sine. The sign in the middle is the same. And then UV, UV, UV. 45, 30, 45, 30. Now, sine of 45 degrees is the square root of 2 over 2. Cosine of 30 degrees is the square root of 3 over 2. Cosine of 45 degrees is the square root of 2 over 2. And sine of 30 degrees is 1/2. Square root of 2 times square root of 3 is the square root of 6 over 2 times 2 is 4 minus the square root of 2 over 4. And combine our fractions together, we get the square root of 6 minus the square root of 2 all over 4. That's it for that one. So when we're trying to find the exact value of these trigonometric functions at these other sort of odd angles, we just have to figure out how to rewrite that angle in terms of angles that we already know values for. Okay, so find the exact value of cosine of pi over 12. Well, that might seem trickier. So we have to think about, now we're talking in radians, so we have to think about angles in radians that when I added or subtract them, the common denominator would be 12. So to me, that makes me think immediately pi over 3 and pi over 4. And pi over 3 is a little bigger than pi over 4, so I think maybe if I subtract them. So we should see if it actually works. Well, what's the common denominator? 12. So pi over 3 is 4 pi over 12, and pi over 4 is 3 pi over 12. And let's check it. 4 pi over 12 minus 3 pi over 12, yeah, that's pi over 12. So that tells me that I can rewrite cosine of pi over 12 as cosine of pi over 3 minus pi over 4. And now I can apply my cosine formula. And the cosine formula is cosine, cosine, sine, sine, and the sign in the middle is opposite. Now, uv, 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 so this is going to be pi over 3, pi over 4, pi over 3, and pi over 4. So, cosine of pi over 3. All right, well, cosine of pi over 3 is 1/2. Cosine of pi over 4 is the square root of 2 over 2. Plus, sine of pi over 3 is the square root of 3 over 2. And sine of pi over 4 is root 2 over 2. 1/2 times the square root of 2 over 2 is the square root of 2 over 4. Square root of 3 times the square root of 2 is the square root of 6. Over 2 times 2 is 4. So finally, that's the square root of 2 plus the square root of 6, all over 4. And that's it. Now before, we verified this cofunction identity, sine of pi over 2 minus x equals cosine of x. Now we're verifying a slightly different identity. This technically isn't a cofunction identity, but it's really similar. Basically, this is an identity that says cosine is just a shift right by pi over 2 of sine, which is true. And you can see that in your Cartesian graphs of these functions. You could also see it by thinking about the unit circle quadrants and how your angles for cosine and sine relate. But here we're just going to use our difference formula for cosine. So we're dealing with cosine again, and I know my formula for cosine is cosine, cosine, sine, sine, and the sign in the middle is opposite. So this is x pi over 2, x pi over 2. Cosine of pi over 2 is 0, so this becomes cosine of x times 0, plus sine of x times sine of pi over 2, which is 1. Cosine of x times 0 is 0, sine of x times 1 is just sine of x. Done. All right, moving on. Now these I consider the really fun problems, and they should kind of be your best friends. Hopefully these will be like the easy problems if you see them, because if you see something like this, your brain should go, oh, that's one of my formulas, right? Cosine of an angle times cosine of an angle minus sine of an angle times sine of an angle. But these are weird angles that I don't know how to deal with, right? We don't know how to draw these on our unit circle and get one of our nice triangles from them. But that's okay, because I should hopefully go, hey, this looks like cosine of u times cosine of v minus sine of u times sine of v. And, oh yeah, that's my sum formula for cosine, with u equal to 57 degrees and v equal to 33 degrees. So that means I can take this expression here and just rewrite it as cosine of 57 degrees plus 33 degrees, which is the same thing as cosine of 90 degrees, which is 0. In other words, these identities work both directions, right? If you have this expression here, right, I can move backwards to the cosine of u plus v form. That's fine. It doesn't matter which way you're going. They're equality, so they're interchangeable. In this case, moving back to that form gives us a nice angle, 90 degrees, that we know how to work with. All right, so now let's take a look at example 5, and this is a similar type of problem here. So remember, when we look at the tangent functions, the sign up top is the one that matches your sum or your difference formula, right? So if you're looking at a sum, tangent of u plus v, get tangent of u plus tangent of v up top. So when we look at this one, that's what we have, tangent of u plus tangent of v over 1 minus tangent of u times tangent of v, and this is tangent of u plus v. And in this case, what is u? U is 28 degrees, and v is 17 degrees. So when we apply our formula here, this should be tangent of 28 degrees plus 17 degrees, which is tangent of 45 degrees, which is sine of 45 degrees divided by cosine of 45 degrees. That's square root of 2 over 2 divided by square root of 2 over 2. That's just 1. Okay, so those were a couple fun problems. Now we'll get to some problems that are a little more involved. So here we're asked to find the exact value of sine of u plus v, given that tangent of u equals 3/4, where u is in quadrant 3, and sine of v equals 5/13, where v is in quadrant 2. So if we're asked to find the exact value of sine of u plus v, that's kind of an automatic hint that you should probably be thinking about the sum formula. So in order to figure out what information we actually need to find, we should write out the sum formula. And the sum formula is sine, cosine, cosine, sine, u, v, u, v. And the sign in the middle is the same. So now, what this tells me is that I need to know what sine of u, what cosine of v, what cosine of u, and what sine of v are in order to evaluate this sine of u plus v. So we're going to kind of do that work off to the side, actually. And that's going to come from this extra information that was given to us. So we were told that tangent of u is equal to 3/4, and u is in quadrant 3. So we're just going to draw our angle u that puts us in quadrant 3. And if we have tangent of u equals 3/4, then 3 is my y value, 4 is my x value, except we're in the third quadrant, so these should both be negative. Which is fine, because negative 3 over negative 4 cancels, gives us 3/4, so that's exactly what we'd expect. Okay, and so we do the Pythagorean theorem here. Negative 3 squared plus negative 4 squared equals r squared. So that's 9 plus 16 equals r squared. It's 25 equals r squared. And that's 5 equals r. So this is a 3, 4, 5 triangle, right? So that gives me all the information I need to find sine of u, which is going to be negative 3 over 5. That's my y divided by r. And cosine of u. That's negative 4 divided by 5. It's my x divided by r. Now, one little thing I want to mention here is that this was a 3, 4, 5 triangle. Now, sometimes they'll give you a triangle where 5 is on one of the legs. So just keep in mind, it's only a 3, 4, 5 triangle, if 5 is one of the legs of the triangle, is the hypotenuse. If 5 was one of the legs, this would not be a 3, 4, 5 triangle. Or if 3 or 4 was the hypotenuse, it would not be a 3, 4, 5 triangle. So be careful, because sometimes you might try to skip that step. Like say you see a 3 and a 4, and you're like, oh, I don't even have to do anything. The other side is 5. But that only works if 3 and 4 are the legs. If one of those is the hypotenuse, then it falls apart. So just be careful about that. Sometimes you will see problems that are designed to trick you that way. Okay, so we now know what sine of u is, and we know what cosine of u is. Now I need to figure out what cosine of v is. I already know what sine of v is. So sine of v is 5 over 13. And we were told that v is in quadrant 2. So when I draw my angle, it should put me in quadrant 2. And sine is y over r, so this is 5 and 13. And what I need is x. So I get x squared plus 5 squared equals 13 squared. That's x squared plus 25 equals 169. That's x squared equals 144. And so x equals negative 12 in this case. It's negative because we're in the second quadrant. So that tells us that cosine of v is negative 12 over 13. And once you've done this, this is all the hard work. Once you've found your values for sine, cosine of both angles, then we just look back at our formula and we plug them back in. Sine of u is negative 3/5. Cosine of v is negative 12 over 13. Plus cosine of u is negative 4/5, and sine of v is 5 over 13. Okay, so we get negative 3 times negative 12. It's going to be 36 minus 20, all divided by 5 times 13, right? That's our common denominator. Now, I never multiply out these denominators until the end because I might be able to simplify them, and it's easier to simplify if the denominator's already factored. So 36 minus 20 is 16 over 5 times 13. 5 times 13 is, so first I should check, is 16 divisible by 5? No. Is it divisible by 13? No. So that didn't do any good for me. Okay, well, I couldn't simplify it, but that's okay. This gives me 16 over 5 times 13, which is 65. All right, well, that's it for that example. Let's go ahead and move on. Okay, so now we have an example that is very similar, but a little bit trickier. Okay, so it's not really any more difficult. It's just that we also have to remember our properties for our inverse trig functions. And if you're rusty on that and you didn't get that down before, then it's going to make it a little bit harder here because we're going to have to use those properties constantly. So the first thing to keep in mind is, okay, I've got cosine of sine inverse of 3/5 plus tangent inverse of negative 4/3. Now, sine inverse, remember these trig inverse functions, they output angles. So we can call these angles u and v and rewrite this as cosine of u plus v. In which case we can start thinking about this in terms of our sum formula. Cosine of u, cosine of v, minus sine of u, sine of v. So now becomes a question of how do I find the values for cosine of u, cosine of v, sine of u, and sine of v. Well, let's start by writing this first one out. U equals sine inverse of 3/5. And I know that if U equals sine inverse of 3/5, that means that sine of U equals 3/5 with a condition. And this is the part that I think typically causes people the most problems, is they haven't remembered these restrictions on the output for their inverse trig functions. So this U value for inverse sine has to be between negative pi over 2 and pi over 2, which tells us that our sine, our angle U, is in either the first or fourth quadrant. The question is which one. But when I look at my value, sine of U equals 3/5, if sine is positive and I'm in either the first or fourth quadrant, tells me I got to be up here. So that makes this 3 and this 5, and I need to solve for x. And of course, that's x squared plus 3 squared equals 5 squared, blah, 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 blah. X equals 4, right? Solve the Pythagorean theorem. It's another 3, 4, 5 triangle. So that tells us that cosine of U is 4/5. And now we use our other piece of information, that V equals tangent inverse of negative 4/3, which tells us that tangent of V is negative 4/3. And of course, the condition for tangent inverse is that V has to be between negative pi over 2 and positive pi over 2. So again, that's the first and fourth quadrant, but here tangent is negative. And I know that tangent is positive in the first quadrant, so that means we've got to be looking down here at our fourth quadrant. So negative 4 would be my y value, 3 would be my x value, and then I need to find r. Again, this is another 3, 4, 5 triangle. 3 squared plus 4 squared equals r squared. R is 5. So I'm skipping solving that algebra. 9 plus 16 is 25. Take the square root, it's 5, right? So that tells me that sine of V is negative 4 over 5. And cosine of V is 3/5. So now that we have all the information we needed, we just go back to our sum formula and we plug it all in. Cosine of U, that's 4/5, times cosine of V, that's 3/5. Minus sine of U, that's 3/5, times sine of V, that's negative 4/5. This becomes 4 times 3, that's 12, over 5 times 5. And a negative 3 times negative 4 becomes a positive 12, over 5 times 5. 12 plus 12 is 24, over 5 times 5. And again, as a general habit, I don't multiply out my denominator until the very end so that I can check my factors individually. Is 24 divisible by 5? No. So I'll just go ahead and write 5 times 5 is 25. Okay, so that's it for this one. Thank you for watching.